or 2 pi, then I've got critical numbers, right? These are all critical numbers, 3 of them. And then how about cosine theta is -1? So where does that happen? Cosine is the x-coordinate. Where's the x-coordinate -1? Right here, at pi. But I already have pi here, don't I? Yeah. So I don't have to look at it twice. This would mean theta is pi. But you see, I've duplicated it. No big deal. Y'all all right with that? That wasn't so bad. Now what if this was something like 0 to 4 pi? Then you would have, what, 0, pi, 2 pi, 3 pi, 4 pi. So you'd have more critical numbers. All right, what do I do with those now that I've got them?
Plug them into the derivative.
How, yeah, if we're going to do max and min, how are we going to do that? Number line, good. Number line's the next step. Number line, plot these critical numbers on your number line. All right, so here's my number line. And I have what? 0, pi, and 2 pi. And this splits my number line up, doesn't it? And I have to pick test points. How many test points will I have? Yeah, so if you look at it the way I drew it right here, I did not extend past 0. Normally I should have, and then I would have a test point over here. And I should have extended past 2 pi and had a test point here, but I didn't. Why? The domain of the original function has me looking just between 0 and 2 pi. So I really only need something here and here. So your choice. Yeah, pick some things that you know, right, that are going to be easy to plug in. Pi over 2 is a good one, and 3 pi over 2. And those guys get plugged into the derivative. So what is f prime of pi over 2? And then what is f prime of 3 pi over 2? All right, let's take our time through this first one. So I'm plugging pi over 2 into this. So I'm talking about, I'm doing -2 sine of pi over 2 minus 2 sine of pi over 2 times cosine of pi over 2. Understand? What is sine of pi over 2? 1. Remember, unit circle, pi over 2 is up here, sine is the y-coordinate. So this is 1, this is 1, this is 0, isn't it? So that's going to kill this whole thing off. And so you just have -2 times 1. -2. What's important to us? That it's negative. That means my original function, f, is going down here. Now you plug in 3 pi over 2. You tell me what you get. Positive 2. Because sine of 3 pi over 2 is -1. And then times -2, that's 2. And then when you do the cosine of 3 pi over 2, it's 0. Right, 3 pi over 2 is down here. Okay, so this is going to be positive 2, which means my original function is going up here. All right, that's it. Where's my function decreasing? From 0 to pi. Where is it increasing? Pi to 2 pi. Do I have a local maximum? No. Do I have a local minimum? Yes. At pi, right? So I could write all the information down, but the only thing that I think is going to be useful to us is the local minimum is happening at this point. Pi, and then what's the y coordinate of that point? Where are you getting that from? What are you going to do with this pi? Plug it in to the original function. All right, let's try it. What's cosine of pi? Negative 1 times 2 is negative 2, right? So we got negative 2 here. What's cosine of pi? Negative 1 squared. 1. 2 plus 1? Wait, was it 2? It was negative 2 plus 1, which is negative 1. Pi negative 1 is a local minimum. We all good? If you're honest with yourself, this is fun, right?
Yes.
If you're honest with yourself? All right, what's next?
So find the critical numbers of
The second one, second derivative. So we have to set the second derivative equal to 0. I'm going to give myself a little more room to work here. It doesn't have one. It never went up and down. If you look at the arrows, it only went down, up, never went back down. Because of our domain restriction. Right, 0 to pi, we were only looking there. It went like this and went like that. So that's it.
But there is a global max. It would like because the endpoint.
Okay, yes, there would be a global maximum on this interval, yes. Unfortunately, that's not what we wanted, but yes, there would be. All right, we ready? Setting the second derivative equal to 0. Dang it, I never went back, I'm so sorry. My first derivative, we set it equal to 0. We never looked at where it was undefined, but it wasn't, okay? It was a nice trig function. So same with this one. Will this one will it ever be undefined? No. Okay, so set it equal to 0. I'm setting negative 2 cosine theta minus 2 cosine squared theta plus 2 sine squared theta equal to 0. Yeah, why don't we just divide everything by 2? Or you could do negative 2. What do you want? I don't care. You want me to do negative 2? Divide out negative 2? All right. So that'll give you cosine theta plus cosine squared theta. Not plus. This should be. Oh yeah. Sorry, it is. Right, like that. We still good with that? All right. Why did I say you took pre-cal? So you could solve that. But I'm going to guess that y'all might be stumped on that.
It's just been a while.
It's just been a while, right?
A year ago, around this time probably.
It's about a year ago.
It's coming back. So
I would have to look at my notes.
Okay, what did we do to solve the last one?
We just broke it down.
We could factor something out, right? Here you can't factor anything out of all terms. But what?
Can't you make the cosine squared theta minus sine squared theta equal to 1?
No, if it was plus, you could.
you just go back and make it a doubling of formula for when we actually when we did the derivative.
So then can you take out the negative?
You mean between them and turn them to a plus? If you try and factor out a negative, it's going to make that plus, but it's going to make that minus. So then it'll still be off.
We'll just be back where we were.
All right, so I could sit here and I could let you go research this and figure it out, or I can just show you, right? So look, what I'm going to do is I'm going to get everything turned into cosine, and the reason why is because sine squared can be converted over to something in terms of cosine, and that's just simply by taking the very important Pythagorean identity, right, and just solving it for sine squared. If I solve this for sine squared, that means just move that over, right? So anytime you see sine squared theta, that's the same as 1 minus cosine squared theta, right? So I'm just going to replace sine squared theta with 1 minus cosine squared theta. Right there. Just be careful with your signs. Cosine theta plus cosine squared theta minus what? 1 minus cosine squared theta, and then equals 0. Do y'all see that? This is the big identity from pre-cal. This is one of the big daddies right here. And now pass the negative through. So cosine theta plus cosine squared theta minus 1 plus cosine squared theta equals 0. Looking better. Ah, crap, I still can't factor out a cosine though. You see why I can't factor out a cosine? Because of that 1. Dang it. No, it's going to work still. Let me just reorder things. I have 2 of those, right? 2 cosine squareds. And then I have a single cosine, and then I have minus 1. Do you remember that from pre-cal? That looks like a quadratic, doesn't it? That actually looks like a quadratic. It's a quadratic form. And so I can factor this into 2 things. It would be, let's see, 2 cosine theta here, plus 1 minus 1? Will that work? 2 cosine squared theta is what I get here. 2 cosine theta times 1 is 2 cosine theta. Negative 1 times cosine theta is minus cosine theta. So when I put those 2 together, I'll get a positive cosine theta, and then negative 1 times 1 is negative 1. So that's it. Does that look familiar to you? If it doesn't, it's been too long or your retention's not that great. You need to go back and look over. I'm here to remind you.
I think when I created them, we replaced them with views.
Yeah, you may have in your pre-cal class when you saw that, you may have done a U-Substitution first. You may have said, okay, look, I'm going to just say everywhere I see cosine, I'm going to replace it with U.
Yeah,
And then you rewrite the problem as 2u squared plus u minus 1 equals 0. Then you factor that quadratic, 2u, and then u, and then plus 1, and then minus 1, and then you replace your u's back with cosines. Yes, I don't know. I wouldn't consider that skipping a step. I would consider that not needing the step. I don't know.
it's just making it easier on your
This right here, needing to do the substitution, I think at this level, you need to work to not need that. You need to see the quadratic without having to replace the u. That's my opinion. I think that's not a stretch. But again, I mean, every math level gets higher, right? So the expectation gets higher that you can do this to here without needing that. If you need it, great. I'm not here to tell you not do it. But I'm not going to say I'm skipping a step. Sorry, I'm just not going to say that. Yeah, it's just a different level. I mean, at some point, do we go back and show basic arithmetic? Like when I divided through by negative 2 here, did I show that? Why?
It's not needed.
No, I skipped a step. You see what I'm saying? Like that, if I actually came through here and did this, and this, and this, and this, okay, then that's how you get to here. Now, you agree with me, I don't need to show that step. What I'm saying to you is that I don't think I need to show this step either. Because that's pre-cal, and to me, that's okay. I'm just delivering the message, everyone, that's all. I'm just delivering the message. This is the expectation of calculus, all right? All right, so now at this point, I have it factored, which is good because I can set each factor to 0. I don't mean to sound arrogant or like an asshole up here. I'm not trying to be. I'm just trying to be honest with what you're presented with. Like this is it. Cosine theta is 1/2. That's from this one. Move the 1 over, divide by 2. And then over here, cosine theta is -1. And those, luckily for us, these are nice, right? See, it's like they make these problems just so special that they're going to work out to be nice things. That's the way it is. Let's talk about this. Where is cosine 1/2? Cosine is the x-coordinate, correct? It's 1/2 here and here. Pi over 3 and
Make sure it's not in the quadrant. It's in quadrant 3. Because that's negative over positive.
what?
Yeah.
Oh, yeah.
It's in quadrant 3.
Cosine can't be positive in the third quadrant. Cosine's the x-coordinate.
But aren't those negative? You're like a negative over a negative.
Yeah, it'd be a positive.
Negative over negative, what?
Yeah, in quadrant 3, it's negative over negative, so it becomes positive.
Okay, so one of two things is happening here. Either my brain just like left the building, or there's some confusion about the unit circle here. Let's figure out which one it is. All right. On the unit circle, if I pick a point, it's cosine of the angle, sine of the angle, right? Where the angle is here. If are you thinking tangent?
Yeah.
Okay. So when you learned tangent, did you learn that little thing?
Yeah.
What was it? All students take calculus, something like that? So this just means all your trig functions, and when they say all, they only mean sine, cosine, tangent. All trig functions are positive here, cosine's positive here, sine's positive here, tangent's positive here. Is that what you were thinking? You were thinking tangent, yeah? You were thinking tangent here and here. Okay,
So you have to have like an x and a y.
that's right.
Or negative, and then it goes negative.
That is correct. Okay, good. All right. I thought my walls of my universe were about to collapse. Okay. All right. Do we all understand that? Off the unit circle, these are common angles. This was 1/2 root 3 over 2. And this one down here is 1/2 negative root 3 over 2. And so we're looking at cosine. That's the x-coordinate. Where is it 1/2? It happens there and there. So what are these two angles? That should be up here like that. Pi over 3, right? This one's pi over 3, 60 degrees. Pi over 3. I need to put my answer somewhere. So theta must be pi over 3. And then, what's this one? 5 pi over 3. 5 pi over 3. And those are the only two answers in our interval. Again, that's why that closed interval makes life nice. No, we're not having to get general solutions here. That would suck. All right, we're still not done. I also need to know where cosine of theta is -1. And that's going to happen here, and that's going to be pi. So from this one, theta is pi. All right. What's next? Yep, number line. And I plot my critical numbers, and let's make sure we get these in order. Actually, I know I'm going to be between 0 and 2 pi, right? Because that's where I'm cutting off my domain. So let's try and place these in there in the proper locations. Pi would be right in the middle. Pi over 3 would be about 1/3 of the way. And 5 pi over 3 would be about 1/3 away from the end. That partitions my number line into some sections here. And I'm just going to put these in blue. Remember, these are like, we can't go past those, right? So how many test points are we going to need? 4 of them. We've got to get one here, and here, and here, and here. What's a good angle off your unit circle that's between 0 and pi over 3. Pi over 6. What's a good angle between pi over 3 and pi? Pi over 2. That's not the only one, right? But that is one. See, what I'm doing is I'm looking at it this way. Here are your 3 critical numbers, right? There they are. So we had to pick something before pi over 3. So pi over 6 is in here. We could have picked pi over 4. Then we went past this one, so pi over 2 worked. Now I need to get something over here, something between here and here. Oh, I like that one. What's that one? 3 pi over 2? And then one more that's got to be squeezed between here and here. 11 pi over 6. 11 pi over 6. What are the things that I said you should get out of pre-cal? Do you see my point? I mean, it's your knowledge of the unit circle and solving trig equations. It helps you here. And it can also hinder you. So you need to go back and just refresh yourself with this if you feel like completely overwhelmed by this right now. And I get to plug all of those into the second derivative. Joy, joy. Which I've completely forgotten what it was, and I've erased it. So f double prime theta was -2 cosine theta. I wrote it down. I think I've got it from here. Right? That was it. All right, we get to plug in pi over 6 first. F double prime of pi over 6 is, oh my goodness. I may as well take a look at this. I'm going to be at pi over 6, right? Pi over 6 is right here. That's the point, √3 over 2, 1/2, just as a reminder. What is cosine of pi over 6? √3 over 2. So I have -2 times √3 over 2 minus 2 times, now what's cosine of pi over 6 again, but squared? So square this. 3/4, 3 over 4. Plus 2, now sine squared. So what's sine of pi over 6? 1/2, and then squared, so 1/4. All I care about is whether or not this turns out to be positive or negative. So let's clean it up. These twos cancel. We get -√3. I could, yeah, this and this. That gives me -3/2. And then here and here, that gives me positive 1/2. These two together? -1? Agreed? It's negative. Which means my original function is not very happy. It's not very happy. Frown. I've got to do this 3 more times. So pi over 2 now. The good news is that at pi over 2 things are nicer, aren't they? At pi over 2, these are easy to work with. Cosine of pi over 2, 0. Cosine of pi over 2, 0. These are gone. And then what's sine of pi over 2? 1 squared, 1 times 2, 2. It's positive. Which means my original function is going up. 3 pi over 2 is another nice one, isn't it? 3 pi over 2? Because that's down here. So at 3 pi over 2, you get, let's see, cosine of 3 pi over 2, 0. 0. Sine of 3 pi over 2, -1, but square it. 1 times 2. Get 2 again. Ah, it stayed positive, didn't it? Tricky, tricky. And finally, 11 pi over 6. Which is right there. What's the ordered pair there? Root 3 over 2, negative 1/2. All right, so let's do that one. This is going to be our last one. And then we're going to be close to drawing it. Maybe. 11 pi over 6. All right, negative 2 times cosine of 11 pi over 6 is root 3 over 2. Minus 2 times cosine of 11 pi over 6. This squared 3/4. Plus 2, okay, square the sine. That's going to be 1/4. Is that the same thing we had earlier?
Yeah.
That's exactly the same, isn't it? Yeah. So it's negative. So it goes down. Concave down. Whew. All right. It is a lot of work.
We haven't even gotten to the Bobby method yet.
Yeah, we haven't even gotten the Bobby method. You're right. All right. I can definitely tell you where it's concave up and concave down, right? But I'm most interested in the inflection points. Do we have inflection points? We do, at pi over 3, at pi, and at 5 pi over 3, right? So I would no. Inflection points are only at pi over 3 and 5 pi over 3. This is not an inflection point, but it is a critical number, right? Okay. So we could plug all those into the original function, couldn't we? And get their values? I'm going to skip that because I'm going to need to do it anyway in a little while. So to get us done here in the next 10 minutes, let me just go straight to the graphing. All right, so when I go to graph, I make sure I have got a nice, clean sheet where I can spread my graph out and show off all this knowledge. Okay.
That's going to be a long take-home.
There we go. Here we go. So I'm going to start at the top here, giving myself enough room. I do know it goes from 0 to pi. I'm going to put these in here. And now let me get all my critical numbers. So from the first derivative, the critical numbers were, who were they? Yeah.
0, pi, and... Yeah.
0 pi and 2 pi. Okay, so the only real one that's in, well, no, I include the endpoints, right?
Yeah.
Yeah, so those are them. And then from the second derivative being 0, we had pi over 3. I remember that one. And what? And 5 pi over 3? And pi, but I've already got pi here, right? Yeah, so 5 pi over 3 will be over here somewhere. Does that cover all of them? From this, I draw straight up. Enough space for 3 rows. And actually, I can't go past 0 or 2 pi, so I'll stop there. Remember, the first row involves the first derivative, the second row involves the second derivative, and the third row is going to be our final kind of picture of what f looks like. Is that what it was? For the first derivative, left of pi is down? That means I'm going to put what here? Down arrow. Here. Down arrow again, right? To right of pi, it was arrows up. Arrows up, arrows up. Are you trying to draw it without my Bobby method?
No, not right now.
You should.
I should master this.
See how this one might be a little harder to do. I don't know. You could try it, but. All right, how about second derivative? To the left of pi over 3, we were frowning, weren't we? Weren't we? It was a frown, and then between pi over 3
and 5.
all the way, right, to here, it was up, concave up. Smiles, happy people. And then after 5 pi over 3, down. Any questions? Come on. Y'all good with that? You sure y'all just exhausted? Both? You're okay though? All right, so let's see. We'll do a fun a little group activity here. It's not going to be that fun. So over here, first table, only one person. You're not allowed to answer. Only one person. What am I going to draw up here? So tell me that in terms of like which side of the what? Right side of the, good. Okay, you want the right side of a frown. Everyone agree? Yeah. Okay, this table over here. You know what, Laura? I hear enough from you. You ready?
The left down.
Left side of this, which is a, yes? What is that right there? Happy or sad?
Oh, that's happy.
Happy. So left side of a happy face. Okay, good. Everyone agree? Right side? See, I told you it wasn't going to be a fun activity. Yes? Left side of a frown. Good. Y'all, everyone agrees with that, right? Although I don't know why I drew that one bigger than the others. I don't like that. Doesn't matter, but.
Okay, when you were doing the 3 pi over 2 for the second derivative,
Uh-huh.
I got 1. I didn't get 2. I don't know.
Into the second derivative?
Yeah. When we were
Can I check it afterward?
Yeah.
Let me check it afterward. Okay. Let's, it's drawing time. And the bad thing is that we haven't plugged these numbers into the original function yet. Not all of them. So here I've got pi. I've got 5 pi over 3. I've got 2 pi. I've got pi over 3. And I've got 0. And my original function, which I erased, is f of x equals cosine x. Was it 2 cosine x? Or f of theta equals?
The original problem,
Yeah, original.
2 cosine theta plus cosine squared theta.
Okay, let's do this. I actually want to plug every one of these into there to get our values. I think we already did it, didn't we? Did we find the local max? Was there? No, we found the local min, didn't we?
Yeah.
Okay, so the only thing we ever plugged in was pi, right? That's the only thing we ever plugged in. But I want to plug all these in. So let's plug in 0. Ready? Cosine of 0, 1. So this is going to be what? 3. So 0, 3 is a point. Okay, what about pi over 3? Ugh. Pi over 3. What is cosine of pi over 3? Half. It's a half. Cosine of pi over 3 is a half. Times 2. 1. Okay, so that's a 1. Cosine of pi over 3 is a half. Squared, 1/4. 1 plus a fourth.
2 5.
5/4? 1.25? Plug in pi. We did that already. What did we get when we plugged in pi?
Negative 1.
Was it -1? Yeah, it was -1. Do you remember doing that? It was a long time ago. 5 pi over 3. What is cosine of 5 pi over 3? It's the same, nope, it's the same as the sine of, cosine of pi over 3. Remember, pi over 3 is there, 5 pi over 3 is down here, cosine is the x-coordinate, same x-coordinate, so we're still going to get 5/4. And then finally 2 pi. And shouldn't I get the same thing as I get when I plug in 0? Right, 0 and 2 pi, same things? So 3. What's the biggest number, largest number that you see here? 3, smallest number, -1. So I need to make sure when I draw this, here's my y-axis. I need to make sure I go up high enough. So here's 3, here's 2, here's 1, here's -1, here's -2, here's -3. My picture will be in red. At 0, my function is at 3. At pi over 3, my function is at 5/4, which is 1.25. At pi, my function is at -1. At 5 pi over 3, my function is at 5/4 again, and then at 2 pi, it's at 3 again. And now it's time to put it all together. We're almost done. I've got to look between this point and this point. I must look like this. So there we go. Between here and here, I need to look like this. Between here and here, I need to look like that. And between here and here, I need to look like that. Damn, that's a lot of work for that, huh? That is a lot of work for that. Was that 40? I think it might have been more. I thought we started at 151. So this was, what was it, cosine, 2 cosine theta plus cosine theta squared. And we were only looking between 0 and 2 pi. I think ours is better. See, there's certain things that you can identify pretty quickly here. Like the inflection point, right? Like where is it happening? We know. Happens at pi over 3, right? Got another inflection point here at 5 pi over 3. All right, so look, graphing functions. What are some things, because this is still in 4.3, right? We haven't moved into the next section called curve sketching. What are some things that we have not included in our graph that might be useful? Like that could get our graph to be even better. That's for parabolas. Yeah. X-intercepts? Doesn't this have X-intercepts? Okay. So let me tell you from the next section some things. Here are the steps that we normally use to sketch curves. First, look at the domain. Then find all the intercepts. X-intercepts, Y-intercepts, find them. Think about symmetry. Is this graph going to be symmetrical? Is it a reflection of itself over the y-axis or not, or x-axis? Entertain the idea of any asymptotes. Does it have any vertical asymptotes? Does it have any horizontal asymptotes? Figure out where it's increasing and decreasing. We did that today. Figure out any local maximums or minimums. We did that today. Figure out the concavity and inflection points. Sketch the curve. So all we're going to do is add some more things onto the top of this.
So basically,
Algebra things.
so basically things that we did out.
That's right. So we're going to combine the techniques from algebra into this, and we will have a final method for curve sketching. It's brutal, isn't it? I mean, this is the way it's done. It was done before computers.
Very short.
Yes, Wolfram Alpha. You just type the function and it graphs it.
Can you take that on the test?
So look, I understand your point of view is probably, like, why do we need to go through all this? I agree. I mean, this is brutal to have to graph this by hand. But the important thing isn't that you could get this graph on Wolfram Alpha. It's Problem solving here. Look, there's a lot of things you have to know to do this, right? You have to know how to do your derivatives correctly. What if you mess up your derivative? It's over, right? It's over at that point. So you have to be meticulous, you have to be careful, right? You get everything, set it equal to 0, you got to know how to solve that. If it's trig, you got to know how to solve it. If it's logarithms, you have to know how to solve it. So there's a lot of different things at play here. And if you want to look at like a topic in this class that kind of brings it all together, this is it. This is the topic. Understand? So it's more of the big picture here is that we're bringing all the ideas from all the math classes that we've learned into like kind of one problem, and yeah. They call those capstone problems. Have you ever heard of like a capstone course? It's like a course that like brings everything together at the end when you finish like a program. It's your capstone. This is kind of like a capstone problem. All right, do your homework. You should be able to do all your homework through 4-3. Have a great weekend. We'll get back into it. I think next week I'll hand you the sketching problems. I'll give those to y'all. Yep. Y'all can get started on them.
The homework is what day? What day is the homework? Or the test?
I think the test is the 15th. I need to go back. It's after the drop date.
Which I'm surprised you didn't.
Well, maybe we'll try and squeeze it in.
I'm just surprised.
I try, but I can't always make
So week and a half.
it fit.
It's a lot of stuff that we have to go over.
My opinion on the drop date is kind of